Hi everyone, and welcome to the Chapter 1 lecture for Chemistry for Life Sciences. So Chapter 1 is all about the basics of chemistry, which is really a lot about measurements. Chemistry is all about matter and taking measurements of matter. So I'll always start my lectures with an outline of the chapter and a funny chemistry cat meme. So math plays a big part in chemistry, and some of the math in chemistry might be math that you haven't seen in previous classes, so just a quick overview of an important topic in math, which is scientific notation. So scientific notation is really just a shorthand way of writing numbers that are either really big or really small. In other words, have a really big decimal number. So the format is C times 10 to the n power, where C is a number between 1 and 10, and n, that exponent, if it's a positive number, it means that the number we're representing is really very large, that it's greater than 1. And if that n exponent is negative, it means the number we're representing is actually very small, less than 1, a decimal. So in order to convert a number into scientific notation, you just move the decimal place, and however many times you move the decimal place, that becomes your n, your exponent. If you're moving the decimal place to the left, then that means that the exponent is going to be positive. It means you have a large number. If you move the decimal to the right, it means that the exponent is going to be negative because you have a very small number. So let's do just a couple of examples here. Oops. So for example, this number here, 23,500, has a decimal point right here that's invisible. And to convert it to scientific notation, we're going to move that to turn this into a number that fits between 1 and 10. And that number would be, if we put the decimal point right here, so it would be 2.35, and then we don't need those extra zeros, so it becomes 2.35 times 10 to the fourth, because we moved the decimal place 1, 2, 3, 4 places to the left. And then here, in this number, we're going to move the decimal place to the right, 1, 2, 3, 4, 5, 6, 7 places to get a number between 1 and 10. 8.4 is between 1 and 10. So 8.4 times 10 to the negative 7th. Did I count that right? 1, 2, 3, 4, 5, 6, 7. We moved it 7 places. And since it's a very small number, and we move those decimals to the right, then we have to make sure that we include that negative sign in the exponent, that it's negative 7. All right, so a couple more to practice here. Let's convert the following numbers to scientific notation. We've got this first one here, 920 million. Our invisible decimal point's right here. We're moving it over 1, 2, 3, 4, 5, 6, 7, 8 places. So in scientific notation, this would just be 9.2 times 10 to the 8th. The second one, we're moving the decimal place over 1, 2, 3, 4 places. And since we're moving it to the right, since this is a small number, that exponent is going to be negative. So we get 3.5 times 10 to the negative 4th. Now we can also take numbers in scientific notation and convert them into regular decimal form. So we'll do that in these two problems here. In this first one, I'm just going to rewrite it so I have room for my zeros. 6.5. All right, and I want to move this 4 places, make the number bigger because this is a positive exponent. So we're going to go 1, 2, 3, 4. So our decimal place is now right here. We need to add some zeros in those spots as placeholders. So our new number is 65000, or 65,000. And in the second example, or practice problem, again, I'm just going to rewrite this out so I have room. So we have 8.34 times 10 to the negative 6, that means this is a very small number, the negative sign. So we're going to move the decimal point in the other direction. 1, 2, 3, 4, 5, 6 spaces. So now I need to put a 0 as a filler in each of these spaces. So I end up with 5 zeros in front of my 8. Or cleaner, written like this. 0.50834. 0.0000834 is this number written out. So you can see that writing in scientific notation just makes these numbers a little bit more manageable to work with. So when we're talking about units of measurement in science, really, we're talking about using the metric system. This is the international system that's used in most countries, but not all countries, and is also the universal units for science. In the US, we have our own system of measurements that are kind of silly, and I stole this cartoon from a math instructor who used to post it on his office door, kind of making fun of the US system of measurements and how arbitrary our units are, like feet and inches and yards and cups and teaspoons, versus the metric system, which is a base 10 system. So you just keep going up in units of multiples of 10. So in US, where we might use pounds or ounces to measure the mass of something, in the metric system we use grams or kilograms or milligrams. In volume, in the US, we tend to use gallons, cups, or fluid ounces even, whereas in the metric system, we strictly use the liters as the base unit. So milliliters, kiloliters are multiples of liters, and so on and so forth. So particularly in the US, when we're doing calculations in science, we may be using some tools to weigh things that report weight in pounds, but we need to convert it into grams. So in order to convert units from one unit to another, we have to do something called unit conversion. So we can convert things within the metric system. So remember, the metric system makes this easy because everything is base 10. So, and then we use these prefixes to indicate sort of multiples. So the base unit has it is the base unit. So a liter or a gram or a meter. Okay, those are all base units. But then we add a prefix like kilo. Kilo, which is represented by a K, means 1,000. So a kilogram is 1,000 grams. A kiloliter is 1,000 liters. Milli, on the other hand, is 1,000th. So a milligram is 1,000th of a gram. In other words, 1 gram is 1,000 milligrams. 1 kiloliter is 1,000 liters, because it literally means 1,000 liters. And a centimeter is 10 times more than a millimeter. So centi is 100th, milli is 1,000th, so that's a difference of 10. So for every 1 centimeter, you have 10 millimeters. It's 10 times bigger. And we can write that as what we call an equivalency. 1 centimeter equals 10 millimeters. So unit conversion is the math that we do in order to convert something from one unit to another. If you measured a room in feet, but you need to convert it to centimeters or something like that. Another name for unit conversion is dimensional analysis. So different textbooks might call it different things. I prefer unit conversion. So what we are always going to start with in a unit conversion is these equivalencies. We need to know, most importantly, how much of one unit is represented in the other unit. So how many milliliters are in a liter, or how many pounds are in a kilogram. All right. We can convert these equivalencies into fractions. And we call these fractions conversion factors because we can use them as multipliers that allow us to convert from one unit to another. So we just took this equivalency, 1 liter equals 1,000 milliliters, and we can make a fraction that says 1 liter is over, or 1 liter per 1,000 milliliters, or 1,000 milliliters per liter. So either way, you can use that. You can make two different conversion factors, basically. And the problem will determine which of these we are going to use. So we can do the same thing if we're converting from metric units like kilograms to US units. And we can turn this equivalency into a pair of conversion factors, into the sort of fraction format. All right. By the way, there is a table of equivalencies in the back cover of your textbook. You don't have to memorize how many pounds are in a kilogram or how many meters are in a mile or anything like that. You can always reference that table. What you do need to know is how to do the conversions. So the reason we can take these equivalencies and turn them into fractions is because in math, whenever you have two values that are the same, and a fraction like 4 over 4 is equal to 1. And since 1,000 milliliters is equal to 1 liter, this fraction here, the value of this multiplier is really just 1. So when we multiply things by a conversion factor, we're not changing the value, we're just changing the units, because the value of this conversion factor, regardless of what the numbers are, is actually equal to 1. So let's do a couple of practice ones. We'll start with an easy one. How many milliliters are in a 2-liter bottle of soda? Many of you could probably do this in your heads. We're just converting liters to milliliters. So when we do unit conversion problems, we're always going to use the same setup. So the first thing you want is to figure out what units you're converting between, and go ahead and write down the conversion factors that you might want to use. So the conversion factors for liters to milliliters are written here. This is the formula for the math setup. We're going to take the given unit, the unit that we're given in the problem, and we're going to multiply it by the conversion factor that has the given unit on the bottom and the desired unit on the top. And that's because when you have two things that are equal on the top and the bottom of a fraction, they cancel out. So our given units, if we arrange it this way, the given units will cancel out and we'll end up with an answer in our desired unit. So my tip is always to set up the equation so that your units cancel out. So the given unit in this problem is that 2 liters. So we start with the 2 liters. Now we're going to multiply it by the conversion factor where liters is on the bottom because we want liters to cancel out. So that is this one right here, 1,000 milliliters per 1 liter. And that way our liters are canceling out. So that unit cancels out. And our answer will be in milliliters. Our answer being 2 times 1,000 divided by 1, which is 2,000 milliliters. So sometimes they're simple, especially the metric conversions. You might be able to do that in your head, but it's really important to master the steps because as numbers get more complicated, or you may have to use more than one conversion factor, it's really important to know the setup. So we're going to keep practicing this. Here's one where we're doing a conversion from US units to metric units, from pounds to kilograms. So again, the first thing we want to do is identify our conversion factors. We look on an equivalency table and we find that 1 kilogram is equal to 2.2 pounds. So we can make either of these. We'll be using one of these conversion factors in this problem. Then we're going to make sure that we set it up in this way. So we're going to start with our given unit. And in the problem, we're given 185 pounds. Oops, there's my tips again. All right, so we start with 185 pounds. And now we're going to multiply it by the conversion factor that has pounds on the bottom and kilograms on top. and that is this one right here. So we plug in the numbers, 1 kilogram per 2.2 pounds, and now we do the math. We multiply the top, 185 times 1, and we divide it by the bottom, divide it by 2.2, and our answer is 84.1 kilograms. All right, so that, when we did that, of course, our pounds canceled out. We end up with just kilograms left, so our answer is in kilograms. So the key tip here is always make sure that you're setting up the problem so that your units are on opposite sides of the fraction so that they will cancel out and you end up with the units that it's asking for. So this is just an equivalency table from your textbook. You can find it in the back cover of the textbook, but also within the chapter. You may want to keep that handy, put a tab in it, maybe print one off offline so that you can reference it regularly for these problems. So we're going to do a couple of additional problems. Doing the first one, a marathon is 26.2 miles. How many kilometers is that? We're going to start with our given unit, 26.2 miles. That's the number we're given in the problem. And we want to convert it to kilometers. So we need a conversion factor that equates miles and kilometers. And we want miles to be on the bottom so that those miles will cancel out. So we looked up on that table and we saw that 1 mile is equal to 1.61 kilometers. So we made that conversion factor. And now 26.2 times 1.61 equals 42.2 kilometers. That's how long a marathon is if you run it in a non-US country. Next one, an adult male's lung capacity is 6 liters. How many milliliters is that? That's one of those easier ones. We're starting with 6 liters. This is just a metric conversion. And we know from the prefix in milliliter that 1 liter, or that there's 1,000 milliliters in a liter. That a milliliter is 1,000th of a liter, so therefore there's 1,000 milliliters in 1 liter. We arrange it so that the liters are on bottom of the conversion factor so that they will cancel out. Our answer is 6,000, milliliters. 6,000, so throw a little M in there. 6,000 milliliters. Last one, a roller coaster has a minimum height requirement of 48 inches. How many centimeters is that? So the number we're given, our given number is 48 inches. We can look at that equivalency table and find out that 1 inch is 2.54 centimeters. So we turn that into a fraction, a conversion factor, where we put the inches value on the bottom so that inches will cancel out, and our answer will be in centimeters. 48 times 2.54 divided by 1 is 121.9 centimeters. Now you may wonder about what numbers you should be rounding to in some of these cases. If you typed it into your calculator, I think you would have gotten 121.93 or something. So in this class, we're not going to go over significant figures. There are rules actually for rounding in science, but they can be pretty strict and really aren't important at this level of chemistry. So my rule of thumb is if it goes past the decimal point in your calculator, just round it to the first decimal point, to one place after the decimal point. If you wrote 122 centimeters on a test, I would not count off for that. Because again, I'm not focusing on appropriate rounding and significant figures in this level course. All right, the most challenging types of dimensional analysis or unit conversion problems are those with dosage calculations, because these often have to be done in multiple parts. So an example here, a doctor's prescription for acetaminophen, which is Tylenol, is 7.5 milligrams per kilogram of body weight per dose. So this is, I like to draw pictures. Feel free to draw them yourself. So here's a picture of the medicine with the dosage. And it says, for a child who weighs 42 pounds, here's my kid who weighs 42 pounds, calculate the number of milligrams to be given in a dose. All right, notice that the dosage, 7.5 milligrams per kilogram, per can almost be read as a division line. You can write that out as a fraction. 7.5 milligrams per kilogram is a fraction. And anytime we have a fraction like that, that's a conversion factor. That's a multiplier we can use to go from one unit to another. Okay, so the first thing we need to do is we need to get this kid's weight in kilograms because the dosage is in grams in metric units, and so we need the weight of the patient to be in kilograms. So the first step is to convert the patient's weight from pounds to kilograms. The patient is 42 pounds, and we can look on the equivalency table and learn that 1 pound is 2.2 kilograms. Oops, I did this wrong. It is 1 kilogram. Just kidding. Kilograms are bigger than pounds. 1 kilogram is 2.2 pounds. So you can correct that. All right, so our pounds now are in the right direction. They cancel out, and we end up with 42 times 1 divided by 2.2 equals 19.1 kilograms is the patient's weight. So now that we know that the patient is 19.1 kilograms, and we know that he should receive 7.5 milligrams for every kilogram of body weight, we do a little multiplication. We take the patient's weight and we multiply it by that dosage. And we make sure that kilograms are on bottom in the dosage. And we learn that this child needs 143.3 milligrams per dose. So that would be the correct dosage for this child. In real life, in real world scenarios, we don't usually give exact dosages. This would probably in a clinical setting be rounded to like 150 milligrams because that would probably turn out to be a more exact measurement. So dosages in medicine are usually not exact, they're rounded, but this is how they are calculated and then rounded. Here's a more challenging one. We've got a prescription for amoxicillin, which is an antibiotic, comes in an oral suspension that is 250 milligrams per 5 milliliters. So that is the dosage, and I'm just going to rewrite it out here as a fraction as it's written in the problem. Now, a patient is prescribed 500 milligrams every 6 hours, or 500 milligrams per 6 hours. How many milliliters should the patient take per dose? So I like to pull out the numbers from the problem and then usually write with a little question mark what it is I'm trying to find. So what I'm going to do, basically what we have here are a number of numbers that we can multiply by each other so that the units cancel out to give us milliliters. We also in this problem happen to have an extra piece of information. So it says that the patient is prescribed 500 milligrams every 6 hours. How many milliliters should the patient take per dose? So we don't care about the timing. We don't care about those 6 hours. All right, so we're just going to ignore that. So in other words, what we have is we have 500 milligrams. We have this fraction here, which is a conversion factor. It's something it's reversible. If we need to reverse it, we can. And we ultimately want to know how many milliliters the patient needs to take. So we always want to start our given unit. The patient is prescribed 500 milligrams. So pardon my slow and sloppy typing here. 500 milligrams times this fraction here that we're going to rearrange because we want milligrams on the bottom to cancel out. And we want milliliters on top because we want our final units to be milliliters. All right, so in this conversion factor here, we've got 5 milliliters and 250 milligrams. So for every 5 milliliters of that amoxicillin suspension, you have 250 milligrams of the drug in it. So now we just do our multiplication. So I'll cancel out our units, our milligrams. And I'm just going to do a little simplification so I can do this in my mind. 250 and 500. 250, if you divide both of them by 250, this is a 2, and this is a 1. So we've just simplified the math here. So 2 times 5 divided by 1, or you could type into your calculator 500 times 5 divided by 250. Either way, you get the same answer, which is flat, even 10 milliliters. All right, well, you might have a second part of the problem that says, well, how many teaspoons is that? Okay, and our conversion factor that we're going to use is that we look at the equivalency table and we find out that 1 teaspoon is 5 milliliters. So if we take that 10 milliliters and we multiply it by this conversion factor, then we get 10 times 1 divided by 5, which is the same as 10 divided by 5, which is 2. Not 2 milliliters now, 2 teaspoons. So perhaps if you're in Canada, you would be directed to take 10 milliliters of the amoxicillin, but if you are in the US, you might be told by your doctor to take 2 teaspoons. Most measuring cups have both units on them, so you would see that they were equivalent. Another type of measurement that's done besides volume and mass is temperature. So temperature has 3 different unit scales: Fahrenheit, Celsius, and Kelvin. The Fahrenheit scale is used primarily in the US. Celsius is the one that's used more commonly internationally and also used very heavily in science and chemistry. And Kelvin is also sort of a specific unit of temperature that's used in specific chemistry calculations. It's what's called an absolute scale. So the bottom of the scale is 0, and then it goes up. So it's only positive values, where on the Fahrenheit and Celsius scale, you can have negative temperatures. So Celsius and Kelvin, if you look closely at these thermometers, they have the exact same dash lines. The size of the degree is the same. It's just offset by a value of 273. So a temperature of 100 Celsius is 373 Kelvin, and 0 Celsius is 273 Kelvin. Okay, but if you compare Fahrenheit and Celsius, if you look at the dash marks, the degree sizes are different. Fahrenheit degrees are smaller than Celsius degrees, so you can't change from Fahrenheit to Celsius with simple addition. You have to use a slightly more complicated conversion. So Fahrenheit is actually 1.8 Celsius degrees plus 32. So it takes into account the difference in the size and the offset. So these are the temperature conversion formulas that we use to convert from Fahrenheit to Celsius, and Celsius to Fahrenheit, and Kelvin to Celsius, etc. You don't have to memorize these formulas. You're free to look them up and use them, but you have to be able to use them correctly. So let's do a practice problem. On a hot summer day in Georgia, where I'm from, the thermometer often rises as high as 102 degrees Fahrenheit, though now with global warming probably even higher than that. What is this temperature in degrees Celsius and degree Kelvin? So if we look at these different equations here, we have an equation here. We can figure out Celsius if we know Fahrenheit. And we can figure out Kelvin if we know Celsius. There's no way to go from Fahrenheit to Kelvin. So we're going to need to figure out Celsius first. So we're going to use this second equation. Degrees Celsius equals Fahrenheit minus 32 divided by 108. So the temperature in Fahrenheit that we're given is 102. So 102 minus 32 is 70, just simplifying this division problem here. 70 divided by 1.8 is 38.9 degrees Celsius. So we figured out the temperature in Celsius. And we can check the validity of our answer with a little bit of sort of mental common sense. So a good thing to do, if I go back to this slide here, is to memorize these temperatures that are listed here. The freezing point of water, the boiling point of water, and normal body temperature on these different scales. So normal body temperature, most people already know, is 98.6 degrees Fahrenheit, which is 37 degrees Celsius. So if you get an answer here that 102 degrees Fahrenheit is 38.9 degrees Celsius, that pans out because body temperature, that's pretty close to body temperature, 98.6 and 37 degrees Celsius. So that answer makes sense. If you got an answer that was like 389, that doesn't make sense. So using those reference points to double check that your answer looks correct is a good way to check yourself. Now that we know the temperature in Celsius, we can use the last equation to figure out the temperature in Kelvin. It's simply going to be our temperature in Celsius, 38.9, plus 273, which equals 311.9 kelvins. Notice that kelvins don't use a degree symbol. We don't say Kelvin degrees. We just say kelvins. So take a little break from the math now and talk about matter, different types of matter. So matter is the stuff of which chemistry is made. Anything that has mass and volume is matter. And we can divide matter into different categories. We've got things that are pure substances and things that are mixtures. The two types of pure substances are elements and compounds, and we'll talk about how those differ. And the two types of mixtures are homogeneous and heterogeneous, and we'll talk about how those are different. Excuse me. So let's start with pure substances. Elements and compounds. So elements are the simplest type of matter. They're made up of only one type of atom. Oftentimes they're made up of only one atom, but the key is that it's only one type of atom. So helium, for example, that goes into balloons. Helium atoms don't like to pair up with other things, so they exist as individual little marbles of atoms. Hydrogen, though, likes to pair up with another hydrogen atom. So pure hydrogen gas is actually H2. It's these little doublets of hydrogen, but it's still just one element. It's still hydrogen. So even though it consists of these two atoms bonded together, it's still an element. Same thing with ozone. Ozone is actually O3. It's 3 oxygen molecules bonded together. But notice in each of these cases, we're just dealing with one element. Doesn't matter how many balls or atoms are in those. If it's one type of element, then, or one type of atom, then it's one element. I over complicated that. Compounds consist of two or more elements bonded together, chemically bonded together. So water is a classic example, H2O. Most people know the chemical formula for water is H2O, which means it has 2 hydrogens and 1 oxygen. So I think it's kind of like a Mickey Mouse molecule. Methane is another one. Methane's a common gas that we burn like in Bunsen burners. And the chemical formula for it is CH4. It's 1 carbon atom and 4 hydrogen atoms bonded together. So that would be an example of a compound. The elements, there's a limited number of elements on planet Earth, and they can all be found on the periodic table. So there's like 118, I think, that exist. This table's a little bit dated, but I still like it because I like the information and the color coding. So some of these have been filled in since this periodic table was published. The periodic table is so chock full of useful information. It really is going to be your new best friend this semester. So you should make sure you have one handy when you're doing homework, when you're watching lectures, because you'll refer to it often. So everything listed on here is a different element. Each of the boxes represents a different element, and we'll get more into talking about these different parts of the periodic table in future chapters. But some things to point out: the color coding. So on the left side of the table, we've got things in blue. Those represent metals. The oddball out is hydrogen here, which is actually a non-metal, but we place it over on the left-hand side of the table, but it really fits better over here on the right-hand side in terms of where the other metals go. And then in between the metals and non-metals, we've got the metalloids. And these are things that kind of exhibit characteristics between those. They're in-betweeners. The periodic table, you'll see, is organized in columns, vertical columns, and horizontal rows. We call these columns groups. So you'll see they each have a group number. There's group 1 or group 1A, group 2 or 2A. Down here we have the B groups, and again over here the A group. So we can use, there's two different numberings for the groups. There's 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, so the A and B numbering system. And then there's just the straight through groups 1 through 18 numbering system. I think the more modern one to use is actually the 1 through 18, groups 1 through 18, but I still am a little old school and prefer the group A and B. So I often will use the A and B groups. There's a functional reason for that. So in this class, we're mostly going to be working with elements that are found in those A groups, which is called the main group elements. And the B group represents the transition elements. So I like to use the A and B grouping for that reason. So groups are columns. Rows, the horizontal rows, are called periods. So this row, the first row is period 1, period 2, period 3, and so on and so forth. So that's a little bit about terminology to navigate the periodic table. All of these letters on the periodic table are the chemical symbols for the elements. So B is the chemical symbol for boron. This table doesn't have names on it, but the one in your that you can print off does actually have the chemical names. Si is silicon. Pb is lead. It was plumbium or something in Latin, which is actually where plumbers get the name from, because they used to use lead pipes to do all their jobs, so they were called plumbers because of the lead. Anyway, notice that some elements have a single letter for a chemical symbol, and some have two letters. And the ones that have two letters, it's always one capital and one lowercase. So that sort of punctuation is kind of important, as we'll see coming up. So a quick little inquiry activity for you to complete is to make sure you can use the periodic table to answer the following questions. First, what is the chemical symbol for phosphorus? So this one isn't great because it doesn't list the names, but the one that you've printed out hopefully does. And P is the chemical symbol for phosphorus. It's right here. So a big part of using your periodic table is just doing it and starting to learn where things are. Because at first it takes a long time to find things, but then you start kind of remembering roughly what area they're in, and it becomes quicker and easier to find things on your periodic table. It says, in which group is phosphorus found, and in which period is phosphorus found? It is in, group is the column, so it's in group 5A or group 15. either way, and it's in period 3, row 3. Is phosphorus a metal or a nonmetal? Well, it's on the right side of the periodic table, and it's in colored yellow, so that means it's a nonmetal. And then this last question, are most of the elements on the periodic table metals or nonmetals? If we look, it's pretty clear that most things are blue, which are metals, which is interesting. Considering that the Earth's crust is made up of silicon and oxygen, which is what sand is made out of, and Earth's biomass is mostly carbon, does this seem surprising? So if we look at silicon and oxygen and carbon, these are nonmetals or metalloids. So a kind of interesting fact for you is that although there are more elements that are classified as metals, there's actually more nonmetals in terms of the amount that's present on Earth. These guys are present in much larger abundance. So there's more numerous types of metals, there's much more abundant amounts of nonmetals on planet Earth. So now we know the chemical symbols for different elements. When we have compounds, we indicate the compound, the chemical formula, and we indicate how many atoms of each element are in that compound. Like we talked about H2O, water, and CH4, methane. So those are what we call chemical formulas. Sometimes we call them molecular formulas, or just the formula. So a chemical formula looks something like this. You have the chemical symbols. So here we have Na for sodium, and S for sulfur, and O for oxygen. And then you'll also notice some numbers there, and these numbers are small and to the right. They are subscripts, all right, and the subscripts indicate how many atoms of that element are found in the compound. So for this compound, Na2SO4, it means that we have 2 atoms of sodium, 1 atom of sulfur, and 4 atoms of oxygen. All right, you might, if you are inexperienced, look on the periodic table for some element called SO. All right, but notice that because this is capitalized, S is 1 letter, O is 1 letter. If it was written SO, the small o, then that would be a single chemical element, except there is no SO on the periodic table, so you'd look for it and then you'd realize, oops, my bad. All right, so there's 2 atoms of sodium, 1 atom of sulfur, 4 atoms of oxygen. Put them all together and you get this compound. All right, we'll come back to compounds and chemical formulas shortly, but that was pure substances, our elements and our compounds. Now for mixtures, the other form of matter. So mixtures can be mixtures of elements or mixtures of compounds, but ultimately they are things that are not bonded together. So compounds are, you'd think a compound is a mixture because it contains multiple elements, but those atoms are physically bonded together. They're chemically bonded together, and you can't separate them. A mixture is different because it contains different things that can be separated. So a homogeneous mixture, homo means same, and so a homogeneous mixture looks the same throughout. So milk looks like this, white, opaque liquid. You can't make out little differences in it. It looks the same throughout. And a lot of jewelry metals like gold or white gold are actually made from blends or alloys of metals. So not pure gold, but gold and copper and silver potentially mixed together. That's what 14-karat gold is. It's not pure gold. But it looks pure. It looks uniform throughout, unless you looked at it through like an electron microscope, or I don't even know what tool you use to look at the different atoms. A heterogeneous mixture is one where you can sort of easily make out some of the different components. So chocolate chip ice cream or a salad of any kind would be classic examples of heterogeneous mixtures. If we're looking one that's a little bit finer, maybe sand on a beach. If you scoop up some sand or some soil, you can actually see little things, little particulates in it. It's not completely uniform. So this is a good, I like this visual to show you the difference between elements, compounds, and mixtures. So here's an example of two different elements. The green ones are made up of single atoms. The purple ones are made up of these doubles, but they're the same type of element, so it's still an element, right? A compound is made up of two different elements bonded together. So the green balls and the pink balls are stuck together. So it's a compound because it contains two different elements bonded. Versus this mixture here, which also contains two different elements, but the elements are not bonded together. They're mixed together. And so you could separate them, physically separate them out. So these are a bunch of different examples of mixtures, of things that contain two or more elements that are separate from each other, and so they can be separated. Let's do a quick practice problem. It just asks you to classify the following matter as element, compound, or mixture. If you classify it as a mixture, then indicate whether it's homogeneous or heterogeneous. So table salt, and the formula for table salt is sodium chloride, NaCl. So it's one atom of sodium and one atom of chlorine bonded together. So it's two elements combined to form one thing. That's the definition of a compound. Nickel. Here's the element symbol for nickel. It's just a single element, so it's an element. Vegetable soup. Well, no matter what kind of vegetables you use in your vegetable soup, usually it's not a soup that's blended and looks homogeneous. It's usually chunks of different vegetables floating around. So we would say that's a heterogeneous mixture. Air is actually a mixture of lots of gases we breathe in, and the most important one for us is oxygen, but oxygen is not actually the most abundant gas in air. Nitrogen, carbon dioxide, hydrogen are also all present, but you can't see that. Air looks, it's all those gases are mixed together very evenly. It's a homogeneous mixture. So matter can exist in different physical states, and the three main physical states are solids, liquids, and gases. And the thing that makes those states different is actually the arrangement of atoms in those states. So in a solid, the atoms are packed really closely together, and they might be wiggling just a little bit, but they're not like rolling around. They're not really moving. They might be vibrating, but they're really packed tightly together. And that's why solids have a defined shape and a defined volume. They are sort of stuck in that shape, and their volume doesn't change. Liquids involve atoms that are fairly closely packed together, but with enough space to sort of roll around each other. They're still close, they're still touching, but they're not so tightly packed that they can't move. And so that means that liquids, since they're still relatively close together and they stay close together, they do have a definite volume, but because they can roll around and flow around each other, they can have a flexible shape. So you could take this beaker of water with let's say 100 milliliters of water in it, and you could pour it into different containers, and the water would take on the shape of those containers, but no matter which container you put it in, it will still always be 100 milliliters of water. And then lastly, you have the gas phase. In the gas phase, the molecules are pretty spread apart, and they're flying around really fast, like bouncing off of each other. And because of that, gases are compressible. So they not only have a flexible shape, but also a flexible volume. If you took this balloon outside on a cold day, it would actually shrink. You can squeeze it and change the volume of that balloon. So matter can change. It can go through either physical changes, which are state changes, where it goes from solid to liquid or liquid to gas, or it can go through chemical changes. And when we, as chemists, are writing about these changes, we use these sort of math formulas that are called chemical equations to indicate these changes. So notice when water melts, when ice melts, ice is solid water. Little S indicates the solid, and when we add heat, it melts into liquid water. So the H2O, the chemical formula, is not changing, just the state goes from solid to liquid. In a chemical change, though, you're getting a rearrangement of atoms and getting new chemical formulas. New chemicals are forming. So in this problem here, the combustion of fuel, octane, in your car, when you drive and you burn gas. All right, gasoline contains octane, which is a liquid, and it burns in oxygen. Oxygen's required for burning, which is a gas. And so you go from C8H18 and O2 to totally new compounds, CO2 and H2O. You've mixed and matched those hydrogens and carbons and oxygens to make new chemical formulas and produce carbon dioxide and water as a byproduct of driving your car. Whee! So when we write a chemical equation, it's very much like a math problem. On the left side of the equation are the reactants, and on the right side of the equation are the products. And then there's a reaction arrow that's kind of like the equal sign in a math problem. And we can read this as a sentence, so we could say the reactants, carbon and oxygen, react to form the product, carbon dioxide. And of course, these little letters in parentheses are there to indicate the physical state of each compound or element. So it's very much like a math equation. And just like in math equations, they have to be balanced. So 1 plus 1 has to equal 2. 1 plus 1 cannot equal 3 or 4, right? So same thing in a chemical reaction. In this reaction, you can't have atoms just disappear. So if we have 1 sodium and 2 chlorines, and they react to form sodium chloride, which is 1 sodium and 1 chlorine, that can't happen. What happened to the other chlorine atom? It can't just disappear. So when we write equations, they need to be balanced. So to balance this, we need to make sure that there are 2 chlorines accounted for on the product side. And we can do that by adding a number in front. We call that the coefficient. So we can say we can make 2 sodium chlorides. But now we have another problem, because now we have 2 sodiums on the product side and only 1 sodium on the reactant side. So we're going to need to double the number of sodiums in the reactants as well. But now our equation is balanced, because now we have 2 sodiums and 2 chlorines, resulting in a molecule that has two molecules of sodium chloride, which means 2 sodiums and 2 chlorines. So to show this in a more visual way, let's do it like this. Here's a visual example. So we have H2, which remember means 2 atoms of hydrogen bonded together. And we have Cl2, which is 2 atoms of chlorine bonded together. And they react to form HCl. As written, this is not a balanced equation, because we have 2 hydrogen atoms and 2 chlorine atoms here on the reactant side, but on the product side we only have 1 of each. What happened to the other hydrogen and chlorine? They don't just poof, disappear. Matter can't just disappear. What we need to do is balance this equation, which we can do by simply doubling the amount of HCl. And essentially what that means is we're putting a 2 in front here. We add this 2 coefficient to mean that we have 2, we can make 2 molecules of HCl from 1 atom or 1 molecule of H2 and 1 molecule of Cl2. So these coefficients, these numbers that we put in front, is what we do to balance equations. We never ever change subscripts. Those are inherent parts of the chemical equation. If we change them, we're changing the chemistry. We can't do that. We can only change the amount of each of these things we have by adding coefficients. So the best way to really learn how to do balancing equations is to use what I call the table method. So you're going to want to list out your elements that you have. So in this problem we have H2 plus O2 is reacting to form H2O. So we have the reactant side and the product side, and we're going to tally up how many of each of those elements we have on both sides of the equation. So the elements in this problem are hydrogen and oxygen. We have 2 hydrogens, H2 means there's 2 hydrogen molecules, and we have 2 oxygen molecules over here. On the product side, H2O means that there's 2 hydrogens and 1 oxygen. So in order to balance this, we need to add coefficients in order to get all of those numbers to be equal. Where did my pen option go? Oh well. Okay, so hydrogen's balanced already. We don't need to change that, so we're going to have to work with oxygen. If we have 2 over here, we need to have 2 on the product side. So I can add a 2 coefficient. That will give us 2 oxygens. But it's also going to change the number of hydrogens because now we have 2 times 2, which is 4 hydrogens. All right? No biggie. We can just add a coefficient on the reactant side. 2 times 2 equals 4. So now we have 4 hydrogens on both sides and 2 oxygens on both sides, and we are balanced. Okay? So really, balancing reactions, it's very much a trial and error process. You start somewhere and you just kind of go back and forth until the numbers in this table are equal. Remember to only change coefficients. The only place you can put a number when you're balancing equations is in front of a chemical substance. You cannot, never, ever, ever touch the subscripts, these little numbers here, okay? Just a quick check that you know how to actually count atoms. So that's kind of critical in being able to balance equations. All right, so remember the subscripts, these little numbers next to the elements, only belong to the element they're attached to. So here MgCl2 means that we have 1 magnesium and 2 chlorines bonded together. N2O5 means that there are 2 nitrogens and 5 oxygen atoms. LiHCO3 is 1 lithium, 1 hydrogen, 1 carbon, and 3 oxygen atoms. Okay, so subscripts only multiply the element they're attached to. Coefficients, the numbers in front, all right, actually multiply all the atoms in the compound. So if you have 3 carbon dioxide CO2 molecules, then you have 3 times 1 carbon, which is 3 carbons, and 3 times 2 oxygens, which is a total of 6 oxygen atoms. The next one, so try these, you can pause and try these yourself, but if we have 2 water molecules, that means we actually have 4 hydrogen atoms and 2 oxygen atoms. And if we have 5 phosphoric acid molecules, then we actually have 10 hydrogens, 1 phosphorus, and 20 oxygens. A couple of typos in this lecture, okay? 20 oxygen atoms. 5 times 4. So let's do one more example, balancing an equation. Actually, I think I have 2. The first thing you want to do is you want to make your table. So you want to list out all the elements, and count how many are on each side of the equation. So in this problem, we've got carbon, we have hydrogen, and we have oxygen. We're just listing the elements, just their symbol. We're ignoring the subscripts and stuff right now. And now we're just going to count them. So on the reactant side, we have 1 carbon, we have 4 hydrogens, and we have 2 oxygens. On the product side, I have 1 carbon, I have 2 hydrogens, and I have 2 oxygens plus 1 oxygen. So oxygen is in both of the products. We have to make sure we count all of the oxygens, so there's a total of 3. 2 plus 1. So now it's like, well, where do we start? Well, let's just start at the top of the table. Carbon is already balanced. So let's move on to another element, hydrogen. Hydrogen is not balanced. We have 4 on the reactant side and 2 on the product side. So let's even those up. If we put a 2 here, 2 times 2 is 4, then that gives us 4 hydrogens. But then we also messed up the number, or changed the number of oxygens, so we need to update that. We have 2 times 1, so we've got 2 oxygens plus 2 oxygens. So that's a total of 4 oxygens now. So now we need to balance oxygen. When we come over here, oxygen is by itself, so we throw a 2 in front. 2 times 2 is 4. And now we have 1 carbon, 4 hydrogens, and 4 oxygens on both sides of the equation. It is now balanced. Hooray! Usually in class I would have you guys stop and practice this one yourself, and I'd go around and check it. But I'm just going to work it for you. One last problem here. We're going to make our table. We're going to list our elements. Carbon, sulfur, and oxygen are the elements represented in this equation. We have 1 carbon, 1 sulfur, 2 oxygens on the reactant side. On the product side over here, we've got 2 carbons, 1 in each substance there. We have 2 sulfurs, S2 is 2 sulfurs, and we have 1 oxygen. All right, so let's just start with carbon. Why not? We start with carbon, we put a 2 here. So now we have 2 carbons. Now we've got to move down the table to sulfur. Sulfur, we have 2 on the product side, we need 2 on the reactant side. So I'm going to put a 2 here. So now we have 2 sulfurs, but we also multiplied those oxygens, so now we have 4 oxygens over here. And oops, why did I put a 0 there? We have 1 oxygen on the product side. All right, so now to make 4 oxygens on the product side, we put a 4 here. All right, so now we can cross out that 1, and now we have 4 oxygens, but we've messed up our carbons. We've changed the number of carbons. So we have 4 carbons plus the 1 here, which is a total of 5 carbons. So if we want to have 5 carbons on the reactant side, we've got to change this coefficient. It wasn't supposed to be 2 after all. It's supposed to be 5. And so when we use this trial and error technique, sometimes we end up going back and changing one of the coefficients we put there. And that's okay. Again, it's back and forth. If you had not started with carbon, if you had started with sulfur or oxygen, you probably would have gotten to the 5 without making the wrong guess first. But there's no wrong way really to do this. You can start with any element and just go back and forth until everything balances out. So we've got 5 carbons, 2 sulfurs, and 4 oxygens on both sides of the equation. And that is the lecture for Chapter 1. Hopefully you feel confident getting through the homework now. If you don't, of course, contact me and get help. See you for Chapter 2.